What's up, everyone? Welcome back. Today we're going to look at a problem that I will categorize it into trigonometry, but also kind of like a calculus problem. And in fact, you may actually see it in a high level course, such as complex analysis, which is starting proving stuff that we have done in lower division courses like in calculus course or like trigonometry course. So what we're going to do is we're going to prove the identity here, which says the nth power of the quantity cosine theta plus I sine theta is equal to cosine of the quantity n times theta plus I times sine of the quantity n theta. And here we're going to provide two different proofs. Again, if there's only one way to prove it, it's kind of boring. So I'm going to do it in two proofs, or I should say two different methods of proving this identity, where theta is of course just, you can imagine that is an angle of some geometric shape, but it's just a variable of representing some values. So in here we can assume that theta can be any value, and you can think that for this moment it'll work for real numbers, but of course we can extend it to the complex number as well. And then for the exponent n, for the first proof, we'll just consider n as positive integer at the moment. Okay, we can also include 0, but for the first proof, we'll just try to take a step back and do something that is easy to understand. Then for the second proof, we can then extend the value of n into any value that we want. So here we go. First proof, we're going to prove it by induction. So when we say induction, here is what we're going to do mathematically. So first, we're going to look at the base case, or we can call it a base step. Usually, we will say that the base step is when n is the smallest number we have. So again, we can have when n is equal to 0, which is very easy to show, because when n is equal to 0, the left-hand side is now going to be everything raised to the 0th power, which is equal to 1. Okay, then the right-hand side, we actually get 0 theta, which is 0, so we end up with cosine of 0 plus I sine of 0. And of course, cosine of 0 radian, it doesn't matter whether it's degree or radian in this case then, is of course equal to 1. And sine of 0 is just 0, so we have 1 plus 0i, which is equal to 1. And therefore, left-hand side is equal to right-hand side, and it means that in the base case, the identity holds. So for most people, they will just move on. And sometimes though, we can actually do a little bit more on the base step to actually give more evidence to it, or make it stronger. So we can see what happened when n is equal to 1. We'll see that when n is equal to 1, the left hand side is just everything to the first power, where the right hand side is of course just cosine of 1 theta plus I sine of 1 theta, and again 1 times theta is just theta. In fact, we will end up with the left hand side is equal to right hand side again. So n equals 1 also works. And it is actually quite trivial. So let's try to do one more base step that is something non-trivial then. Let's say when n is equal to 2, so that we'll have a strong argument. So what happened when n is equal to 2? Let's substitute it. We will end up with the left hand side is the sum cosine theta plus I sine theta, all raised to the second power. So now we're going to expand it. So we'll just use the square of the sum formula, which is a plus b quantity squared is equal to a squared plus 2ab. And here we'll switch the order of a and b, which is fine because they are commutative, meaning that the products will the result of the product will not change even if we switch the order. And then we'll add b squared, and in this case we'll have I squared, which is -1, so we need to switch the sign into minus and end up with negative or minus sine squared theta. Good. And now if we look at the right hand side, on the right hand side of the identity that we need to prove, we will end up with cosine of 2 times theta plus I sine of 2 theta. And now we need to use the trigonometric identities that we have learned, which is the double angle formula. For cosine, of course, we can get cosine square minus sine square, where for sine of double angle, it will give us 2 times sine theta cosine theta. And don't forget there is an I, imaginary unit, in the front as well. So we will get 2i sine theta cosine theta. And now if we compare between the left hand side and right hand side, we actually get the same result. And therefore, this identity holds when n is equal to 2 as well. Good. So now is the second step when we need to do a mathematical induction, which is known as the inductive step, or some people will just call it the induction. So what do? We will now assume that the identity here, or the expression that we have, holds for all integers up to k. So what does that mean? We will I should put it this way: for all integers that is up to n. So we will say that for all the integers starting from 1, 2, or maybe we can include 0 in our case because we just proved it, all the way 3, 4, and all the way up to n minus 1 and n, this identity actually holds. Okay, so this is our setup, and k is actually well, I should actually label it this way. K is an integer, or a positive integer here. Then what we need to do here is to show that this identity also holds when we have n plus 1 in our expression. Okay, then if k is equal to n plus 1, we now get the following. Now we start with the left hand side. We will get cosine of, and again, usually it will be better if we try to make it as a direct proof from one direction all the way to another instead of splitting into 2 parts, but it is okay. Sometimes that will be split into 2 different parts. So here we have this expression here. cosine of theta plus I sine of theta, all raised to n plus 1 power. But that gives us cosine theta plus I sine theta times the remaining part, meaning that we're going to take out one copy out of n plus 1 copies, and then we'll just leave the remaining n copies aside. So in this case, we'll actually get first, we'll keep the first factor as it is. We still have cosine theta plus I sine theta. Now for the second one, since we have already assumed the identity holds for all the integers up to n, meaning that when we have n as our exponents, this identity holds. So this means that we can actually replace the right hand, not the right hand, the second factor into the right hand side of the identity. So I'm going to put a big bracket here. We will end up with cosine of n theta plus I sine of n theta, like this. Great. Now we're going to multiply it, expand it out. So we have the first, we can FOIL it to get the first one is cosine theta times cosine of n theta. And then we have, let's put the last term first. Last term will be I times I, give us negative. And then we have sine theta times sine n theta. Perhaps it'll be better to put a parentheses here, so we will be able to tell it without questioning. Good. Then we still have the outer term and the inner term. And if we try to take the outer term, we have I times cosine theta sine of n theta, like this. And for the inner term, we will have I times sine theta cosine of n theta, theta cosine of n theta. And of course, if we put these two together, there is a common factor, I, that we can factor out. So we can just end up with some expression like this. Good. So now we're going to use the trig identity again, because we have cosine of first angle times cosine of second angle minus sine of first angle times sine of the second angle. And that is actually known as the sum of two angles for a cosine function. So we will end up with theta plus n theta. And now for the other parts, we of course also have the I, and we have cosine of first angle times sine of second angle plus sine of first angle times cosine of second angle. And that, by the trig identity, we will get sine of sum of the two angles, like this. So perfect. Now we can just add the two angles together. We have theta plus n theta. So how many copies of thetas do we have? N plus 1. Very good. So we can just put it like this, n plus 1 times theta, and put the brackets here. Good. Similarly, here we will have sine of n plus 1 times theta, like this. And this, ladies and gentlemen, is the right hand side that we're expecting with. Therefore, now we just show that no matter what n we choose, it holds true, then the next number, n plus 1, is gonna be true at the same time. So we can just call it in the inductive step by saying that since it will hold true for all the integers or all the positive integers up to some point, and then it will yield the next one. It will continue we can continue argue that it will hold true eventually for all the integers n. And that is it. That just shows that this identity actually holds for all non-negative integer n, including n is equal to 0. And that's the first method. Alright, I know it is long, but here is the second method. The second method will actually allow us to extend the n from non-negative integers all the way to real numbers, or even we can extend it to the complex numbers. But first of all, we need to use the identity here, which is actually known as the Euler's identity, and you probably will have learned it in Calculus 2 course when you learn about the Taylor series, which says that e to the I theta is actually equal to cosine of theta plus I sine of theta. And again, you can just prove this identity here, the Euler's identity, by using Taylor's expansion of the left-hand side and the right-hand side, and get the three different terms and show that the identity holds. But assuming that this is already true, then the proof will get a lot easier. Here comes the proof. Starting off with the left-hand side, we have cosine of theta plus I sine of theta, all raised to the nth power. So by the identity, everything inside of the parentheses can be rewritten as e to the I theta. And don't forget, we still need to raise it to the nth power. Then, by the exponent's property, when we have an exponent right outside of another exponent like this in parentheses, we can just take the product of those two. So we get e to the I n theta exponent. Good. So now we can use the Euler's identity one more time, but instead of having theta, we will just replace theta by n times theta. So that now when we plug it to the right hand side, we will get cosine of n theta plus I sine of n theta. And again, this would be the right hand side that we want in the identity. And one more thing is that in the Euler's identity, e to I theta, theta is not limited to be any integer or any specific value. It can be any real numbers or even in complex numbers. And therefore, now we can actually extend the n into any real numbers we want, or even into some complex numbers that we want, because now we are using the Euler's identity to help us build whatever we want. For this n, we can just replace n into something that is irrational, or maybe something that is non-real complex numbers, and then this identity will still satisfy. That's it. Pretty cool, huh? Well, I hope you all enjoyed this video, and if you do, please don't forget to like, and then you can also subscribe to my channel to find out more of my other videos. I'll see you guys next time.